Kinetic molecular theory and the ideal gas law describe a simplified model for explaining the behavior of gaseous substances. Throughout our previous discussion, though, we have been leaving some things out when we described gases this way. In real life, no gas is perfectly ideal. The relationships given by the ideal gas law are a little too simple to accurately capture how gas particles will behave in all conditions. Most of the time, these distinctions are small, but they illustrate some important chemical principles that tie back to our previous work with atoms and molecules. It's time to take a brief look at how we model real, or non-ideal, gases. There are two main assumptions in kinetic molecular theory that are technically not true to life. First, we've been assuming that all of those attractive intermolecular forces that we spent so much time on don't matter in the gas phase. Particles of an ideal gas aren't supposed to interact with each other except when they collide. We know that's not really the case, and that's the first correction we're going to have to make. It's worth thinking about when this will really start to matter, though. Most of the time in everyday life, the gas molecules we encounter are widely dispersed, meaning that there's a relatively small amount of gas in a relatively large amount of space. Under these circumstances, it's fairly unlikely that gas particles will spend much time around one another, so whatever attractive forces exist won't influence the overall behavior of the gas very much. But say you had a different scenario, like a highly pressurized gas cylinder. Here, we have a ton of gas particles squeezed into a tiny amount of space, and now it's not so rare to have a bunch of them in close proximity. You might imagine that the IMFs between particles will start to have a real effect here. Depending on how strong they are, those forces are actually going to put a check on the amount of pressure felt by the walls of the container, since the gas will end up looking more condensed than we'd normally expect. The second assumption is that gas particles don't have any significant size to them. We know this isn't really true either, and that the size of an atom, mostly defined by the electron cloud, can vary depending on the element you're talking about. Again, we'd say that this is only going to be a problem for the ideal gas model when there's a whole lot of gas compressed into a certain amount of space. This one sort of works in the opposite direction from our earlier point. When things get really crowded, the gas is eventually going to start taking up more room than our ideal gas law would predict, because gas particles aren't actually volumeless points. To account for these issues, we can essentially just take the ideal gas law and rewrite it with some corrections added in. This gives us something known as the van der Waals equation, and it includes some new terms that address the two issues we just discussed. The first term is here to correct for intermolecular forces. Hopefully we can see that this part of the equation will be pretty negligible when the number of moles of gas is relatively small and the volume is relatively large, but that it will start to get more and more important as n goes up and v goes down. The parameter a here is an empirical value that relates to the strength of the IMFs between gas molecules. Gases with strong IMFs, like water vapor, will have a large value of A, whereas gases with weak IMFs, like helium, will have a small value of A. The second term we see is here to correct for the volume of the gas particles. Similar to before, we can see that it's going to have a greater influence as we add more and more moles of gas to a given volume. The parameter B here will have large values for big things like organic molecules and large noble gases, and smaller values for compounds and monatomic gases that are made of elements with smaller atomic radii. Again, the values of both A and B here are empirically determined values, meaning they come from physical experiments and aren't numbers that you're ever going to have to determine from scratch. But based on what we've discussed here, you should be able to guess what sorts of molecules will have relatively larger or smaller A and B values. A molecule of F2 will have very small values for both A and B, since it's a nonpolar molecule and both atoms have very small radii. A gaseous atom of krypton might still have a small value for A since it's also nonpolar, but a larger value for B because it has a larger atomic radius than the two fluorine atoms combined. That's all for now on this topic. Hopefully you have a better sense now of the assumptions we've been making about gas behavior and what we have to consider when we correct for them. Thanks for watching.